Hello, this is Dr. Strickland. In this video, we will investigate the relative stabilities of alkenes. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So one of the things that it's going to be important for you to be able to do is to classify alkenes by their stability. And in general, a more substituted alkene is a more stable alkene. With the di-substituted alkenes, steric strain is also an important factor. But how do we know that? We do science to figure it out. So first, we're going to show you which is more stable than what, and then we'll take a look at how we know. So remember that if you have an R attached to anything on a general structure, that it stands for the hydrocarbon rest of the molecule. I don't know if I made that up, the R being for rest of or not, but it certainly is an R. So if it's a tetrasubstituted alkene, you have bonds to carbons from both of these sp2 hybridized carbons. So 2 from the left-hand sp2 carbon, 2 from the right-hand sp2 carbon. With the tri-substituted alkene, you still have 4 positions, but only 3 of them are taken up by carbons, and 1 has a hydrogen. With the di-substituted alkene, there are 3 possibilities. The 2 alkyl portions can be oriented trans. They can be oriented cis. Or they can be geminal, attached to the same sp2 carbon. So this is called a trans disubstituted alkene. This is a cis disubstituted alkene. This is a geminal disubstituted alkene. And you can see that the trans is more stable than the cis disubstituted, and the cis disubstituted is about the same stability as the geminal. The trans is least stable because it's got those 2 alkyl parts as far apart as possible. With a monosubstituted alkene, you only have 1 alkyl piece attached to 1 of the sp2 carbons and 3 hydrogens in the other 3 places. Now, we're going to take a look at 3 reactions and their enthalpy changes to see what the scientific basis for saying this is. So this is the most stable alkene, and this is the least stable kind of alkene. Okay, so 1, 2, and 3, and we'll have equations, and then we're going to look at some graphs down here at the bottom of the page. Let's say we had 3-methyl-1-butene. So I'm going to draw its condensed structural formula. 3-methyl-1-butene. And we're going to do a catalytic hydrogenation with 1 mole of hydrogen gas in the presence of that most common catalyst, palladium on carbon. And we find that when you do this reaction, this is the product that you get. So this part of the molecule looks all the same. And then in this part, we've added a mole of H2 across the pi bond. So 1 hydrogen goes here and 1 goes there. So you can see that what's happened is that this has turned into that. And when you're talking about this guy, they find that the enthalpy change, and we're going to call that delta H1, is minus 30.3 kilocalories per mole. Because whenever you're doing a whole column of numbers, you can put the units at the top, or you can put the units with each value. And that's absolutely fine either way. So what if instead we had this alkene, CH2, CH3, CH2, CH3. We have this guy, And we subject it to the same conditions. Then we make the very same product. Because we've added the hydrogen to a different part of that molecule. See that? So it's these two carbons that are involved. And that's how they end up. And the enthalpy change for this process is minus 28.5 kilocalories per mole. And remember, the minus sign tells you how much energy is released. All right, so what if we had this alkene to start with? One more possible place we could put it and still end up with the same product. Because that's the point, right? When you're doing an experiment, you only change one variable, which means that in all three of these cases, we're mixing the initial alkene with hydrogen gas in the presence of the palladium catalyst, and we're forming exactly the same product. All right, so in this case, these two carbons that are involved. All right, so the enthalpy change for this third reaction is minus 26.5 kilocalories per mole. All right, so I want you to pause the video, write the names of each of these three alkenes, and then classify them as monosubstituted, disubstituted, or trisubstituted, or tetrasubstituted. All right, so pause the video and do those two things, and then come on back. All right, welcome back. So this first one up here is 3-methyl-1-butene. And because when I look at those two sp2 carbons, when I see three hydrogens and only one carbon that's attached to an sp2 carbon, this is a monosubstituted alkene. So this one down here is 2-methyl-1-butene. And it's a disubstituted alkene. It's actually a geminal disubstituted alkene. And then this one down here is 2-methyl-2-butene. And it's actually a trisubstituted alkene. See, there's one hydrogen there, but three carbons. All right, so we're going to see how these experimental results are going to help us sort out who's more stable than who. So this is the free energy diagram for these reactions. And we can put them all right on the same graph because they all make the same product. So I've got them in order with their free energy changes, and I want to show you where they are. So this is the free energy change delta H3. That's the minus 26.9. Ah, got an error up here. Okay, so fix this. It should be 26.9. This one, minus 28.5, this is the amount of energy that's released during that second reaction. And then the minus 30.3 is the largest amount of energy released, corresponds to our first one. Okay, so since they all go to the same place, we can see that this one had to be the most stable because we've got the smallest gap between the energy of the reactants and the energy of the products right here. And the only way that can happen is if this is the most stable alkene. So the next biggest gap is from here to here. That means that this guy, our disubstituted, is the next most stable. And then finally, the biggest gap tells me that our monosubstituted alkene was the least stable one. But these are the experiments that were done to generate the results that produce this scheme that we have at the top and that we'll use. But it's all based on experimental evidence. It's always important, most important, I think, to follow the evidence and see where it takes you. All right, so that's the basic story on the relative stability of alkenes and where that all comes from. If you have any questions, please send them to me.